I'm going to be speaking today about the transport and acceleration of greater than 300 MeV solar protons. I appreciate that there's quite a wide range of interest in the crowd, so I'm going to start with more of a gentle introduction to solar energetic particles, that should read, before moving on to some observations of SEP events, and then some modeling of SEP events, and then just some general conclusions. So SEPs, or solar energetic particles, are high-energy ions and electrons that originate from the sun. They are typically associated with large solar flares and coronal mass ejections. Just try to give an impression of that in these images. So on the left we have, let's see if this works. On the left here we have a solar flare. You can see this bright thing in the center. And then shortly after, I don't know if you'll be able to see at the back, but there's some particle noise on the image from the solar energetic particles. Similarly, on the right here, we have a coronal mass ejection in the kind of quiet state here, and then during the coronal mass ejection, you get this large amount of particle noise from the solar energetic particles. So SEPs typically arrive at Earth within, well, in some cases minutes, it can be a couple of hours. Oh, wrong way. So SEPs can be accelerated to relativistic energies up to GeV, the protons can. I know this isn't necessarily high energy for a lot of you in the crowd, but for solar protons, GeV is. Why do we care about them? Why do I care about them? So these high energy protons can cause a whole range of hazards and risks to people on Earth and in space. So increased radiation doses to astronauts, air crew, it's a big problem for airlines. Obviously damage to spacecraft electronics as well as on the ground. So in 1989, there was a large power cut in Quebec caused by a large solar eruptive event. They can also induce radiation storms on Earth, which are measured on this scale from S1 to S5. So S5 are the most extreme, they're also the most rare though. So some SEPs are accelerated obviously up to hundreds of MeV and greater in energy, and some of these are capable of reaching Earth and ground level and are therefore called ground level enhancement events, which I'm sure some of you are familiar with in the crowd. So I've just shown a little diagram here on the top of, so a solar proton hits the atmosphere or the magnetosphere, some complicated cascade reaction, which I'm not going to go into, and then the neutrons are detected down at ground level by this network of neutron monitors, which there were a few talks on yesterday. There's another typo here. It's actually 73 GLEs have been recorded since the 1940s. So they're quite rare, but obviously they're these very powerful SEP events, which are very interesting to study. I've just included this neutron monitor profile of two particularly powerful GLEs we have in modern records. So in red, we have GLE 69, which occurred on the 20th of January 2005, and then in blue, GLE 42 on the 29th of September 1989. I'll refer back to these two GLEs quite a lot in this talk. You can see the percentage increase for both of these was exceptionally large. So I've tried to kind of group the outstanding questions and the main fields of research in this area into three categories. So first we have, how are the particles accelerated? You know, where do they come from? Where are their source regions? Secondly, how are they transported through space? And thirdly, what determines if an SEP event actually occurs at Earth? So I'm going to briefly go through each of those questions. So firstly, how are the particles accelerated? So I mentioned that SEP events are generally associated with large solar flares and coronal mass ejections. So for coronal mass ejections, the acceleration mechanism is predominantly thought of to be shock acceleration. And with solar flares, it's predominantly, you know, magnetic reconnection from the field lines in coronal loops like this. So with the coronal mass ejections, the SEPs are generally associated, especially the higher energy SEPs, are generally associated with very fast CMEs, up to, I think, the largest one we have is over 3,000 kilometers per second. They're also, the larger SEPs are also associated with very wide CMEs. So I've got a nice image here on the top right of this halo CME with a width of 360 degrees. For the solar flares, Again, the large SEPs are associated with large solar flares. So on this image here, you can see this very bright point on this image of the sun is an X-class solar flare. So solar flares are ranked according to their soft X-ray peak. So there's 5 different classes, logarithmic classes, sorry. So you have A, B, C, M, and X. M and X are the largest ones, and those are the ones that are typically associated with these SEPs. Secondly, we have how are they transported through space. Obviously, these SEPs, they're charged particles, ions and electrons, so they're guided through the heliosphere by the interplanetary magnetic field, which, as it originates from the sun, takes the form of a Parker spiral. But between, obviously, the sun and the Earth, there are lots of other things going on that can affect the transport of these SEPs. So I've listed some of these: shocks, turbulence. There's a lot of research going into these fields at the moment. I think we had a talk yesterday about interplanetary CMEs, things like that. I've also put down here the heliospheric current sheet. It's something I'm going to be talking about a lot today. So just briefly, the heliospheric current sheet is the boundary or the divider between the oppositely directed magnetic field as it comes from the sun. So this heliospheric current sheet, obviously, towards solar minimum, the field is a bit more calm and the current sheet is quite flat. But as we approach solar maximum, this tilt angle, it increases, it becomes very chaotic, the current sheet. So finally, what determines if the SEPs are detected at Earth? So I've said quite extensively that large SEP events are generally associated with large solar flares and coronal mass ejections, but that's not an exclusive thing. Not every large flare, not every fast CME produces an SEP event. So we really want to kind of nail down the conditions under which SEP events do occur to improve our forecasting abilities and mitigate the risks associated with them. So one thing we do kind of know about these events is because of the Parker spiral, there's a kind of zone of good magnetic connection, where if we trace back the foot point from the Earth to the sun, it tends to occur in this, around west 60 on the sun. So we know events that happen here have a greater chance of causing SEP events at Earth. So that was my brief introduction. I'm now going to move more on to actual observations of these SEP events. So there are quite a lot of instruments which are capable of detecting SEPs around 100 MeV or lower. However, as I've said, I'm interested in more of the greater than 300 MeV range. Unfortunately, there are not a lot of data sets and instruments that are capable of detecting these higher energy protons. One such data set is the HEPAD instrument on board the GOES spacecraft. So GOES has been operational since, I think it's the early 80s, and the HEPAD instrument itself extends up to several hundred MeV, so it's a great tool for studying these events. I've shown here on the right in red is a HEPAD profile from GLE 42, which I mentioned earlier, from September 1989. And then in blue is the IMP8 GME data from the same event. So you can see quite a large data gap. We looked at this data set, but it was pretty useless for studying these big events. So within this data set, we identified 30 SEP events, 26 of which were GLEs, 4 were non-GLEs. They all occurred between 1989 to 2017, so they span 3 solar cycles, 22, 23, and 24, I think. And then within that data set, we compared the SEP event data, so things like the peak flux and the fluence, with properties of the associated GLE, coronal mass ejection, and solar flare. So I'm just going to briefly talk through some of the results from them. So starting with the comparison of the SEP and GLE properties. So I've just mentioned that we got our SEP properties, the peak flux, and things from the GOES HEPAD data. For the GLE data, we've been using, obviously, the neutral monitors. So on this image on the right-hand side is one of the GLEs with, a very nice defined profile. The different colors are the different neutral monitors that observe this event. And for each GLE, we used the neutron monitor profile with the largest percentage increase. So in this case, it would be the blue profile. Conversely, on the left-hand side, we have the neutron monitor data for GLE, I think it's 57 from 1998. You can tell the profile here is, not very well defined. It's hard to make out, well, a peak or an onset or any of those, useful information. So we've excluded ones like this from our sample at the moment. So finally, some results. So this top panel here on this plot, these top two plots show on the x-axis the maximum neutron monitor increase from the GLEs in our sample versus the peak flux from the GOES HEPAD data in the two high energy channels in black and red. So you can see immediately, there's a very nice correlation. The correlation coefficients are 0.98 for channel 12 and 0.99 for channel 14. So, despite this whole kind of reaction that goes on from the protons down to the neutrons on the ground level, there's still this very nice correlation. And I will point out this kind of outlier looking event in the top right is GLE 69, that 20th of January 2005 GLE, which is, excluding GLE 5, was one of the largest GLEs we've recorded. Similarly for fluence, the correlation on the bottom plots here for the people online, the neutron monitor fluence on the bottom versus the fluence from the GOES channels on the y-axis. So you can see, again, there's a nice correlation, the correlation coefficients between 0.72 and 0.9. So moving on to the SEP and CME properties. So we have different things to consider with the CMEs. There's things like the width as well as the velocity. When we looked at the width, we basically found that they were pretty much all halo CMEs, which is fairly common for GLEs, obviously. You can see here this nice halo CME from the Halloween storms of October 2003. It was a series of very large solar events. So we've mainly been looking at the CME velocity instead. I will say at this point, there is, our events date back to the 1980s and 90s, and there's quite a big lack of CME data in this time, so we did have a reduction in our number of events there. So on the x-axis here, we have the CME velocity. The top panels are the peak fluxes in the 3 GOES high energy channels, and then the bottom panel is the fluence from the 3 high energy channels. So you can kind of see almost immediately there's not very nice correlations anywhere here. So in the top panel, we have correlation coefficients, around 0.24 down to 0.18 as the energy increases. These are not remarkable at all. When we look at lower energy studies, of which there are quite a few, so less than 100 MeV, we find correlation coefficients around, between 0.6 to 0.4, so they are quite a lot stronger at lower energies. When we look at the fluence, we find a similar thing, so correlation coefficients between 0.35 decreasing to 0.19 as the energy increases. And then in lower energy studies, it's a lot stronger between 0.6 and 0.45. You can see there's quite a nice range of CME velocities though. I think the smallest one we have is about 938 kilometers per second, extending up to, I think it's 3,200 for GLE 69, that one that occurred in 2005. So this final bit on the observations is the comparison of SEP and flare properties. So we took most of our flare information from GOES soft X-ray data. So we looked at things like the peak in the soft X-ray flux, the duration, the location of the flare, obviously I mentioned that's important, and also the proximity to the current sheet. So again, you can see a nice flare here from the October 2003 storms. I think this one was an X17. The largest one we have in modern records is an X28. That did not produce a large SEP event at Earth, which I always think is interesting. So again, we have a similar plot here with the logarithm of the flare intensity on the bottom, with the peak flux in the 3 GOES high energy channels in the top row, and then the fluence or the event integrated flux in the bottom panels. So you can see most of these SEP events are X-class flares between an X1 and an X10. There are a few M-class flares. I think that's, there's a couple of, I think it's 3 GLEs and 2 SEP events in that little group. So you can see that, again, the correlations aren't great. So in this top panel for the peak flux, we have correlation coefficients of 0.37, 0.41, and I can't see what that says, but it's about, I think it's 0.38. And then when we look at lower energy studies again, the correlation coefficients are around 0.55 to 0.63. So again, they're weaker than in lower energy studies. The correlation between the peak flare intensity and the event fluence, this time are actually comparable to lower energy studies. You know, close to 0.5, which is what we see at less than 100 MeV. So next I took, so this plot here in the top left, for those of you online, the logarithm of the peak flux versus the flare intensity. And I looked at how the polarity of the IMF affects things. So I briefly described earlier about the heliospheric current sheet separating the inward and outwardly pointing magnetic field lines. So here we denote an A+ polarity describes an IMF where the magnetic field points outwards in the northern hemisphere and inwards in the southern. For an A-, it's the other way around. So here in this bottom plot, we have the A+ events marked in red and the A- in black. So you can see for any given flare intensity or flare magnitude, the A+ events tend to have a lower peak flux. So sticking with the kind of heliospheric current sheet IMF angle, we also looked at the spherical angle between the flare and the closest point on the current sheet for each event. So here we have the SEP events in blue, of which there aren't many, and the GLE events in red. So you can see most of the events, most of the GLEs, 50% of them, occurred less than 10 degrees from the current sheet. We explored the current sheet and the drifts, the related drifts along it quite extensively in a paper that was published recently. If anyone is interested, please go check it out. This is one of the plots from it on the right-hand side. So this is the histogram of all M7 flares that occurred between 1976 and 2020, I think it is. So again, this spherical angle between the flare and the closest point on the current sheet. In red, we have the flares in that time period that are associated with GLEs, and in blue, we have all other flares. So you can see we get quite a nice peak close to the current sheet. I think it's 44% of these GLE-associated flares occurred less than 10 degrees from the current sheet. We did some statistical analysis of this with a 2-sample KS test, and it suggested that the 2 samples were drawn from different distributions. Some brief conclusions from this observational study. So we have greater than 300 MeV events, SEP events, show weaker correlations with flare and CME parameters than are seen at energies less than 100 MeV. The correlations between SEP and neutron monitor data, conversely, are nice and strong. Most of our greater than 300 MeV SEP events are associated with ground level enhancements. But in general, we'd like more high energy data, please, to study these events. So my final section, I'm going to give you a whistle-stop tour of the modeling we've been doing of SEP events. So like I said before, it's quite a diverse area of research. There are a lot of models of SEP events that simulate a whole range of different things. We've kind of stuck to exploring the heliospheric current sheet in this case. So we've been using this 3D test particle model, which includes drift effects due to the curvature and gradient of the Parker spiral, as well as the current sheet drifts. I will point out that no perpendicular transport associated with turbulence is included yet, but we hope to include it in the future. So we've modeled 17 GLEs that occurred between the 80s up to 2017. and we modeled each of them with and without a current sheet to see how that affected the drifts. So you can see there was quite a range of polarities. So, well, most of them were A-. We had a few A+ ones here. That was mainly due to how we selected the events. We had a range of solar wind speeds. And then these columns are things to do with the angular distance. So the column number 5 here, delta F, is this distance between, the flare and the current sheet, which I've just been talking about. Delta E is the angle between the Earth and the current sheet, and phi is the angle between the flare and the Earth's foot point. So I mentioned just now about the polarity. The polarity of the field we've seen does affect the drift direction along the current sheet. We've seen that in previous studies, and we also see it here. So if the flare is close to the current sheet and the polarity is A-, we'll get a lot of drift towards the east. And if it's A+, we'll get drift towards the west along the current sheet. So I'm just going to briefly talk through one of these events. If anyone wants to see any more, please go look at the paper. So I'm going to talk about Geely 42, which is the September 89 event. It was a very nice, large Geely. So we have the source surface map here from the Wilcox Solar Observatory for this Carrington rotation. You can see the neutral line here. The current sheet was very chaotic, very disturbed, and our fit to this current sheet is in red, which we include in our model. You can see the Earth's foot point, this red circle, and the flare location, the yellow star, were both very close, if not on the current sheet. And because we approximate this as an A-, we're expecting, drift towards the east, up and towards the Earth's foot point. So some results. So we inject 3 million protons instantaneously and allow them to do their thing for 72 hours. And then we map the cumulative proton crossings at 1 AU. So this top map is with the current sheet, and this bottom map is without the current sheet. So you can see in this top map, from the injection point, we get a lot of drift very efficiently up and over towards the Earth's foot point. And in the bottom, we obviously get no particle crossings at Earth. So we can extract these flux profiles at Earth and compare them with observations, which is what we did. So let me take a second to talk through this plot. So in red, we have the observed heat pad profiles from GOES between 300 to 400 approximately MeV. And then every other profile is a simulation result. So these left-hand panels are the results with the current sheet included, and the right-hand panels are without the current sheet included. So you can see almost immediately that no matter how we vary these parameters, the models with the current sheet always return the better fit with the observations. So things we varied include the injection width in this top panel. In these results, the injection width was 10 by 10 degrees, but we varied it up to 60 by 60 in all our simulations. And then this middle panel is the power law index, and this bottom panel is the mean free path. So you can see, there's very efficient travel towards the Earth along the current sheet throughout the heliosphere when the flare is close to the current sheet. And we saw this in all the simulations where the flare was within about 15 degrees of the current sheet. So I've just reiterated that here the current sheet is a dominant mechanism affecting the particle transport in this simulation, and a flare close to the current sheet leads to more current sheet transport. So this was Geely 42, which was the September 89 one. In the paper, I've also discussed Geely 69, which was the January 05 one. This plot from earlier, I've tried to reproduce it in our simulation results. So you can see there's some similarities here. There's a nice agreement. The peak, the counts per second, the peak flux for Geely 69 was higher, like it is in the neutron monitor data. I just thought this was a nice plot to include. The model fits the observations the best or well for events with the source locations close to the current sheet. So just wrapping up, The conclusions from the modelling side of things, we have that the current sheet plays a significant role in distributing energetic particles throughout the heliosphere, and it's necessary in over 70% of our modelled events, so over 70% of those geoleads in that table. The particle transport along the current sheet is most efficient when the flare is within 10 degrees of the current sheet. So the events where the current sheet was less relevant was the events where the flare was further from the current sheet. This was the minority of events. So going back to that histogram, 44% of geoleads between 1976 and 2017 were within 10 degrees of the current sheet. More generally speaking about SEP events, so greater than 300 MeV events pose the most risk to manned spaceflight and technology. So naturally understanding more about the nature of SEP acceleration and transport through further observations and modelling will hopefully aid in our ability to improve forecasting of these events. You know, these events are very rare. We've had 73 geoleads for the last 80 years. I always say hopefully we'll see more of them. Some people obviously don't want to see more giant events, but as we approach solar maximum, hopefully we'll get more data to look at. Thank you.